Hi everyone. This is the second session following the SOFC guide, the simulation for the SOFC guide. Last time we saved the step one when we gave all the boundary conditions. We will continue from the same point. Previously, we imported all the report definitions. In this session, we will define all the report definitions by ourselves. So in order to define the report definitions for calculating the fuel utilization of hydrogen and oxygen, we want to implement the formulas given in the tutorial manual, and given the mole base for hydrogen consumption. This is the formula for the mole base, which is the partial pressure of the hydrogen multiplied by the volumetric flow rate, total volumetric flow rate divided, and this is actually derived from simply from number of moles of hydrogen in minus number of moles of hydrogen out divided by the total number of moles given at the input. And if we substitute n is equal to pv over rt, where v is the volume, but volume flow rate, because it is a flow rate, it's a continuous flow rate, that's why number of moles is also in the flow rate, that we can replace it by q. So where q is area multiplied by the velocity, the bulk velocity. So we will, in order to implement these relations, we need to define all these report definitions in our system. So we will go ahead and define all these report definitions, but make sure that when we are defining the mole fraction at anode and cathode, at the anode side we have got hydrogen, so we will go to the species mole fraction of hydrogen both for the anode inlet and anode outlet. But when we go towards the cathode side, we will give the mole fraction for oxygen. And make sure these are all area weighted averages, the fuel variables, and the surface that are to be selected. So this is the table defines all the parameters that we need to input in the Fluent. So we'll go ahead and describe all the report definitions ourselves and give the expression for calculating the fuel utilization and oxygen utilization. After that, we will go ahead and solve it and compare our results with the previous result. So let's get started with it. First, we will define the areas. So we should go to report definition, new, surface report, and area. Click on area, and this is like as already mentioned in the manual. We'll follow the manual. Area, inlet, anode. So area, inlet, and node. This, and uncheck the report file and the report plot. Take the area, and the inlet is inlet anode, inlet at anode. Okay, you see we got the first area, inlet, anode. Now we can copy it from here, copy, and it gives -1. So but we'll just and make it outlet of anode. Make sure you uncheck these report file and report plot, and this corresponds to outlet of anode. Okay, likewise we will define inlet and outlet of anode, and likewise we will define for inlet of cathode. So we'll copy it again, and instead of, we'll give inlet cathode, inlet cathode. Okay, now similarly like this, outlet of cathode. Okay, so with this we have defined all the areas for anode inlet, outlet, cathode inlet, and outlet. Now we will move on to temperatures. So temperatures we will define by new, surface report, and area weighted averages. So now from now on these are all area weighted averages, and we will give it the definition T bulk inlet anode. This is the name. Uncheck these. Temperature, static temperature, inlet anode. Okay. Now copy, outlet anode, likewise inlet cathode, and outlet cathode. Following the same procedure, give all these definitions that we have seen earlier. Give all these definitions, U, P, mole fractions. These are the field variables and on which surfaces, and these are all area weighted averages. So give all these, and after giving all these, we'll continue from there. Why? So we have defined the velocities. Velocity we defined as magnitudes, velocity, total velocity magnitudes. Now we are going on to define the P, the pressure. Make sure we are defining the absolute pressure. So at inlet and node, when we are defining the pressure, it's not static pressure. Make sure it's not static pressure. This is the absolute value. So this is important that you select the absolute pressure. So from name also, this is P absolute at inlet and node. Okay, and likewise we will copy it, P absolute at outlet. Now we do the same procedure for cathode. Now we are defining the mole fractions for hydrogen and oxygen at anode and cathode. So for this we have defined the first hydrogen mole fraction at the anode inlet. For we will define it for species and mole fraction. There are two options, mass fraction and mole fraction. Make sure to specify mole fraction of each two at anode inlet. Okay, and we'll copy it the same for outlet of anode. Okay, likewise we'll give for oxygen also, but we will select O2 mole fraction inlet and cathode. Sorry, this should be mole fraction of oxygen. Make sure you change this. With this we have defined all the required report definitions that take the that access from the simulated results. Now we want to give the expressions for fuel utilization and oxygen utilization. So go on to the named expressions and select new. We'll give it the first expression is given by fuel utilization, fuel, and we are solving in mole percentage. For mole percentage expression, and for defining it we can directly define it by selecting here, open the brackets, and from the report definitions, now Q is made up of U and A, the bulk velocity and the area. Q is equal to UA, so we will multiply U bulk inlet and node inlet multiply by the area of a node. This is Q, and now the partial pressure of hydrogen. Partial pressure of hydrogen is total pressure multiplied by the mole fraction of hydrogen. So we will multiply both total pressure and mole fraction. P absolute inlet anode multiplied by mole fraction H2 mole fraction inlet anode. So, and this all is divided by RT. In the expressions, if you go on to the formula for fuel utilization, now you'll see that R is common for all the terms, so R can be cancelled out. So if you cancel out the R, so the only remaining term is T, which we will do that. and now divided by T bulk anode inlet, all these terms and minus the outlet terms. Now the outlet terms, outlet anode multiply by area multiply by P absolute anode outlet multiply by mole fraction of hydrogen divided by temperature, and bracket close. This whole term is divided by the inlet, so we can copy paste it. And for percentage expression, we multiply by 100. So click OK. Now you see we get the expression for fuel utilization mole percentage expression, and you can see the expression also. Now similarly we will give the oxygen utilization mole percentage, new, and we'll give oxygen mole percentage, and again we will define it the same way from report definitions. For defining the Q, UA, U is the bulk velocity at cathode. Now we'll take the cathode side, multiply by area of cathode, pressure, multiply by, now we go to the oxygen mole fraction, so, and now divided by the temperature terms. All this will be minus area outlet cathode, P absolute outlet cathode, multiply by O2 mole fraction at the outlet, divided by temperature. So now this is the numerator side, and whole divided by the inlet. You can copy paste it, and again for percentage expression multiply by 100. Okay, but right now we cannot add it into the report definitions or the monitors. If we try to add the right now fuel utilization and oxygen utilization, we cannot add these into the report plot. So if we even try to add them into the report plots, for example, let's say we follow the tutorial manual and try to enter H2O2 utilization. Now right now there is no report definition with this. So what we need to do is we need to define a report definition that defines the fuel utilization and oxygen utilization. So we will give new, and instead of surface reports we'll go to expression. We give it expression base, and the name is fuel utilization mole percentage. Now we cannot give this name, so if you try to give it the same name, fuel utilization, and uncheck this, okay. Alright. So sorry, we can give this name exactly mole percentage, and likewise we'll give the same for oxygen utilization, new expression oxygen utilization, mole percentage, and expression oxygen utilization. Okay, so now we have got oxygen utilization, and if you follow the tutorial manual, we have got further report definitions also. So for that purpose we need to define a few more report definitions. Now those report definitions are mainly cell current, cell voltages, uh, and minimum mole fractions. We'll look into that also. So for defining the first, let's define the minimum temperatures. That is relatively easier. So we'll go on to the first set and define the temperatures. So we'll set new. Now this is not a surface report, this is actually a volumetric report, and we want to get the minimum and maximum temperature. So we'll go to the volume report, minimum temperatures, and we'll label it T minimum anode, and this is the minimum temperature, static temperature in the anode side. Okay, likewise you can copy it, and instead of min we call it maximum, and it's maximum static temperature in the fluid anode. Okay, sorry, we will. Okay, now you see we got the minimum and maximum temperature for anode, and we will copy it, the maximum at sorry minimum at cathode, minimum temperature at cathode, maximum at cathode. Now for after that we will go on to fuel utilization, we have already defined, and now the minimum mole fractions. This is important to note that for while defining the minimum mole fractions, we do not define it on the volume, but we define it at the electrolyte surface report, phase at phase at minimum is to min mole fraction, and this is important at anode. For H2 we will get the phase at minimum species mole fraction of H2, and the surface which is of our interest is actually the wall electrolyte at the anode side. Obviously for oxygen it will be the cathode side. We will do it right now. Okay, and you can copy it. Now if you want to check the minimum mole fraction of O2, obviously it is not at the anode side, it will be at the cathode side. So for the cathode side we should select the cathode side, not the anode side, and minimum mole fraction of H2, no, O2, mole fraction of O2. So now this is set. So with this we can give the minimum mole fraction of a fuel and oxygen at anode and cathode. Now we will go on to currents and voltage. So we will define the cell current, new surface report. Now this is actually an integral. The total current is actually the integral of the flux, the current density. So we'll take the integral and call it current tab, cell current at the current tab, integral user defined memory interface. Yes, this is interface current density, and now we will take wall current tab. I want to select the current tab. Okay, now we can copy it at voltage tab. Integral. The last thing we want to define is the cell voltage. For this we will define new surface report, and this is again area weighted average. Cell voltage, as we discussed previously, cell voltage will only be we can only get the voltage from the cathode side, not from the anode side. So we'll take area weighted average of the user defined scalars electric potential at the current tap side, because this corresponds to the while we were making the geometry and doing the meshing, this is defined at the cathode side. So we will select the current tap over here. Okay, now we are ready to give the report monitors. If you go to the report plots and new, again H2 and O2 H2 O2 utilization, uh, fuel utilization and oxygen utilization. H2 O2 utilization, for every iteration we'll get the plot. Okay, new plot, T minimum and maximum, and we can write min and max temperature, and we will select all these four. Okay, minimum and maximum temperatures, and now we want to select the minimum fuel and oxygen at the surfaces. H2 and O2 minimum mole fractions, minimum mole fractions for H2 minimum mole fraction at anode, and likewise O2 minimum mole fraction cathode. Okay, after this we have the cell currents and cell voltages. New current on taps, cell current, voltage tap and current tap, and finally we have the cell voltage. Okay, now we will do one additional things, because we want to get it's easy to plot, and we will have a report file, so we can have new just report file 0, that's okay. Not, we can get for every maybe let's say 10 iterations, just to compare a few if we want to tabulate things. So cell current, cell voltage, fuel utilization, H2 minimum, O2 minimum mole fraction, minimum mole fraction, and then now we'll set fuel utilization and oxygen utilization. Okay, and now we are ready to set the run. So we'll go to the solution and standard initialize, and with initialize we'll give it 550 iterations at the first condition. At the first condition we gave it to converge the solution for the minimum current. Okay, and we'll calculate it. With this we have got the first solution completed, and we'll continue for in order to compare the values. We'll just go and give it a value of 0.7 volts. If you go to the converter and convert it to 0.7, okay, and 50 runs is enough to compare the values for fuel utilization. So our main target is to compare the values from the fuel utilization. We have solved the solution for 0.7 volts, and now we will compare it with the values that we get in the tutorial. So for the fuel utilization, now we can get the value of 64.4, and in the tutorial at 0.7 volts the hydrogen utilization is also 64.4, and the oxygen utilization that we get is 20.1, which is the same as mentioned in the tutorial. So this concludes our session for today. We input all the report definitions by ourselves, gave the expressions, and solved for this. Now, one more thing that we intended to give it the report files. So, in the report files are actually available in the same directory. I'll show you. So, if we give it this simulation videos. Now this is the report file, and we can report file open it with notepad, and you can see we can open this file in the form of notepad, and then later on whatever we want to do with it. So you see we get the voltages and all the corresponding. Thank you. This concludes our session for today. Bye.